Hello everyone, welcome to the OS2 and we have briefly covered the introduction of the structural analysis last time, and today we are gonna review our learning outcomes from the statics such as apply the load and reactions and determinacy. So let's get it started. So the aim of this short podcast is to remind you our learning outcomes about the applied load, load path, free body diagram, equations of equilibrium and rigid body, and etc. So let's think about what was the learning outcome from the statics. So we have actually learned a lot, but basically we'd like to highlight on those things. The rigid body matters, and all the times we discussed about the applied force and the moment that was the applied load, and the free body diagram we call the FBD is truly important. And we also discussed about the how to solve all those engineering matters. Once we establish the free body diagram, we should know how to resolve the engineering methods. So equations of the equilibrium by setting the force x and force y equal to 0, and the moment is also 0 if we are dealing with the 2D the system matters. And structural modeling and idealization or the simplification is needed, and the statistical determinate methods. So free body diagram. So what was that? And actually for these we need to understand the applied load, force, or the moment. Once we define the applied load, then we will further discuss about the reactions, which means that applied load and based on the given boundary condition we can calculate the reactions, and at the same time, based on these, we will discuss further about the the internal behaviors. So in the case of applied load, we have the uniformly distributed load and the concentrated load CL, and based on these we could do the structural idealizations. So rigid body matters. So all the time in statics we discussed about the applied load to our structural system here, and this is the applied moment, more than 2, 3, something like that, and you can see the boundary conditions as well. So that was the rigid body. So in physics, how they define it, rigid body is a solid body in which deformation is 0 or so small it can be neglected. So therefore the distance between any 2 points in this the structural element given point on the rigid body remains constant in time regardless of the external forces or the moment. So it is here the distance between 2 points does not change. This is the definition of the rigid body. Of course, in this module, structural analysis, we will discuss about the deformable bodies. That is the main difference. And in the case of deformable body, and therefore we learn about the statics by not allowing deformation and the solid or the marine mechanics. So we focused on all types of the stress matters such as normal stress, tension and compression, and shear, and including the torsion matters. So in this module, again, we will cover the detailed structural analysis techniques by having solid understanding of the statics. Especially we should be able to understand the applied load reactions so that we can establish free body diagram and solve it by equations of equilibriums. So for the first step, structural idealization or the simplification is required. So let's look at it. So structural idealization, that refers to the process of the replacing an actual structure with a simple system. So here, the structural idealization could be defined as a process here, but therefore we engineers who provide the optimized engineering solutions to our clients, always recognize and focus how to provide the best engineering solutions and the outcomes by considering the accuracy or the safety and the time and the cost methods. So effectively, we engineers should be able to provide the best outcome to our customers. So for example, if let's say we have the gold here as a structural material, why not? We know that it is quite expensive, but technically we can utilize it. Why not? So for example, if our client wants to construct the ship using gold, why not? It is technically no issues. It is available, but cost matters. So if let's say if I ask you whether you can calculate these yellow the area in 5 seconds, how you could do that? I will give you 5 seconds, and let's see how to resolve these engineering methods. 5, 4, 3, 2, and 1. So time's up. So how do you think that? So this is quite complex shape, isn't it? And our customer clients ask us to calculate the area in 5 seconds. This is the given criteria for us engineers. So how to get that is actually think about it. So because we have only 5 seconds here, so let's assume that this is our centroid, for example, and briefly just measure the distance, like set the radius here, and then we can make the circle, for example, like that. Sorry for the drawing, but based on this, we can think about area of this circle that should be pi r square. So we get the radius, just simply measure it. It's like the 5 centimeter, for example, so that we can get the area of these. And within 5 seconds, like this, way we can provide the solution to the client. Of course, we would not say that this is the perfect solution, but within these criteria, 5 seconds, this might be considered as the relatively nicer solutions, isn't it? So it is like this. This is one of the modeling technique, or the simplification the way. And all the time we engineers, again, we should be able to provide the effective, cost-effective solutions like accuracy, time, and the cost methods. So structural idealization, and in general, this is the example of the typical civil structures we call the bridge. And you can see here, this is the boundary condition. Look at that. It seems like the roller system. It could be moved slightly to the left, to the right, and the followed by the boundary condition. We should focus on the applied load as well. So this is the typical shape of the vessel ship structures. And if we focused on the midship section, this is the one, the frame spacing is about 4 to 6 meters length here. And I will discuss about the stiffened panel. So of course we will focus on these, the deck area. So this is the extracted stiffened panel. This is that is the combination of the plate and the stiffener. In this case, this is the flat type. So we call the plate and the stiffener combinations, so that if we focused on these, this could be considered as the plate here and the stiffener. So how do you think that in general this ship structure is subjected to the vertical bending moment, like the hogging or the sagging bending moment? So especially in the sagging condition, the deck area will be compressed, so that in this way the modeling could be made. So in this case, once we apply the actual compression here, so this is the combination. The shape looks like the simple beam method, isn't it? This is the plate and the stiffener and the length, so that we will extract this part only and apply the actual compression. So this is one of a good example of the simplifications. And if you focused on the applied load again, that is the concentrated load or the point load, we also have the distributed load as well. So this might be the good example. This is the beam and the simply supported boundary conditions, and they have applied the two different amount of the load, 300 and 500 kilonewton. The shape is like the concentrated load, and in the case of distributed load, of course, we have the uniformly distributed load and the non-uniformly distributed load. So this is the uniformly distributed load, like the 5 kilonewton per meter, and this is a triangular shape, and the non-uniformly distributed load applied to the beam. And of course, we can change the applied load shape, like the second order, third order is up to the conditions. So how to calculate the total force, that is truly important for us structural designers, and where it acts. So two things you can see here. Like in this case, we should understand the total force that is related to the total area, and the position is related to the centroid concept. Of course, we have learned all those things from the statics. So in this case, we can see that total area is not difficult to calculate the triangular or the rectangular or something like that. So if we focused on this is the triangular shape. Of course, the area could be considered as the B and the H times 1/2, so that this will be the total force from the distributed load. And centroid, of course, in this case we are only talking about the x-axis only, so that is around here. This is B, and the 1/3 that should be around here, isn't it? So the centroid should be like that. So based on this information, we can simplify it like this one. So total force will be applied at here, B/3. B is 10 meter, and total force, the area, could be calculated like that. So different shape, we can get it like this, and of course like that, or that. So you have your own books and look at the appendix part. It might not be difficult for you to find this kind of information. So let's have 2 or 3 simple examples so that you could understand better. So this is the beam conditions, and applied load is the uniformly distributed load, 5 kilonewton. And how to get that? So the question is to calculate the total load applied to the beam, and they want us to find the positions as well. So total load, that is exactly the same as the area total, isn't it? So this is the area total, this is 10 meter, and this is 5 kilonewton per meter. So that area should be 10 times 5, so that is 50 kilonewton is applied. And the location, that is the centroid. Centroid is actually, this is the rectangular, so that it should be at the center, isn't it? So it will be like here, the 5 meter distance, and total is 50 kilonewton is applied to the beam. So which means that this distributed load could be replaced by the centroid concentrated load, 50 kilonewton at the centroid here. So the other example is number 2 is like here, distributed load, but this is actually a triangular shape. So in this case, let's calculate the total load, that is exactly the same as the area total. This is 10, and this is 10 kilonewton per meter. So this is 1/2 times B is 10 and height is 10, so that we can get 50 kilonewton. This is same as the previous example, and this is the total load, and the location, that is like here, this is 1/3 and times B. B is actually the length, so that that will be 10/3 here, and total amount of the force, that was 50 kilonewton. So this is quite simple, isn't it? So if we focused on further, moving on to example number 3, applied load is the concentrated load 300 kilonewton, as well as we have the distributed load 5 kilonewton. So in this case, how to get the total load? So that is actually, let's try to utilize the combination of the 300, the total load, that will be like 300 kilonewton in this case, times the length, that is 12, so that should be 60 kilonewton plus 60 kilonewton, so that total load should be 360 kilonewton. At the same time, we can think about splitting it into two to use the superposition method. So the first one is 300 kilonewton case, and the other one is distributed load case. So this is like 60 kilonewton plus, that's all. So this is at the centroid here, and this one is location is 3 meter, this is 6 meter. So in this case, we can calculate all the methods. So superposition method has been highlighted here. And in the case of load path, this is also interesting. You can see the civil structures, and the floor load is applied, and that will be transferred to the slab and the girder, and the column will be compressed, and the foundation and footing. And in the case of the suspension bridge here, the slab will be loaded, and the hanger, suspender load will be transferred, and the main tower here, and foundation by the cable. So this is kind of the load path. In the case of marine structures, ship structures, you can see here, and due to the difference between the cargo load and the self-weight and the buoyancy force, the ship, this is the main types of the apply the load to the ship structures, and this is the section of the ship. And once we apply from here, the shear force will be applied, so that the midship section, you can see the shear flow like that. Of course, this is the oil tanker, and this is bulk carrier. Please bear in mind. But anyhow, we are talking about the shear flow from the shear force applied. Of course, we can plot the shear force diagram and the bending moment diagram, so that we can get the maximum bending moment. We can see apply the bending stress distributions. And of course, if we are talking about the beam methods, it is pretty much similar like as ship structures. That is reason why in the case of ship structural engineering, this shape could be considered as the simple beam structures. So today we discussed about the apply the load and the load path and the free body diagram and how to solve it using the equations of the equilibrium and rigid body methods. Of course, in this module, structural analysis, we will further discuss about the deformable bodies and structural idealization techniques. So that's all for today, and thanks very much.